It's actually really nice out today, and it's a lot nicer than it was in here when I recorded, what was that, yesterday I think it was, parts 1 and 2, but anyway. Let's get started on the third and final episode, Applying Size and Proportional Plots. And the rants of episode 1 and 2 were kind of leading towards this. If you don't know what a proportional plot is, how it's going to be used here is very simply. Basically, we are going to take data sets of identical items at different populations. In this case, it will be Sasquatches within North America, and we're going to divide them between West and East. But before we get there, proportional plots, unlike bar diagrams, which usually have the scale on the X and Y axes, these don't have scale, and they're usually represented by circles. Now, here's a good example of a series of data sets represented by circles that are accurate and representative of reality, and we're going to get to that. But basically what it does is, say I have an island here, and on the east half of this island, I have a population of, say, 10 flowers. They're the same species as the 25 on this side. We're just keeping it simple. This isn't anything in particular, and neither will the Sasquatch example be. You know, if I had 10 times this would be a lot busier, but you can see that even though they're the same species, they kind of cluster on these opposite sides of the island for whatever reason. Now, I want to represent the populations of both of these sitting here and doing a contour plot or something like that, which would actually be more accurate. But if I just want to inform you of something like how many flowers over here as opposed to over here, how people usually do that is they will have circular plots of a proportional size, and they'll either put the number within it or in a legend somewhere. But the point of doing this is to put it actually on the map so you can get a picture like this here, okay? So as you can see, all that data was compressed into a circle, and you try to get it about as centered as you can within the area of wherever these things are, flowers, I guess, in this case. So those two circles represent populations of flowers, and these should be, even though they have numbers in them, they should be to scale. And what do I mean to scale? The population here on the west end of the island with 25, the circle should be 2.5 times larger than this one. Well, what do I mean by that? That was what all that dimensional stuff was about. You are representing these two circles here as relative sizes to one another. So we are going to be dealing with area of a circle. Now, a lot of people, what they'll do is they will misrepresent the circle size, not really because of any fault of their own, but because they're knocking it down another dimension. And I'll go through the Sasquatch example with you here now so you can get a better idea of what I'm talking about. Okay, we are going to be working with two separate populations of the same species of hypothetical, non-existent, black-haired Sasquatches. We're going to use colors to represent the populations, which will reflect in the circles. It is not the color of the Sasquatch. The green will be referred to as the Western Sasquatches, and the yellow will be referred to as the Eastern Sasquatches. And this map here, you can see North America with a big red line through it. Our Western Sasquatches all live to the left or west of that line, and all the Eastern Sasquatches live to the right or east of that line. And these are our populations. That's my symbol for Sasquatch right there. I made it up, kind of a crooked dollar sign thing, I guess. But in order to make circles of proportional plots, because proportional plots are usually dealing with different ratios of data within the same data set. You're not doing things like comparing mountain lions to traffic on I-80. You'd be comparing mountain lions in this region to mountain lions in that region, something like that. We are going to have to decide how big our circles are going to be. So we do the factor thing that we did before. And this is an easy calculation. You've seen me do this before. We obviously have more green than yellow Sasquatches. All we have to do is divide our more populous by our less populous one to get a factor. And in this case, we have 100 green Sasquatches and 50 Sasquatches here. We just divide them. And as you saw in the last video, we can cancel both units because we have we're dealing with Sasquatches. So we're just going to cancel the Sasquatches, but we can also drop one of these zeros, which you guys have seen as well. And we're basically dividing 10 by 5. And what that gives us is a factor of 2 times greater. So we have twice as many green Sasquatches as yellow ones. Okay, now that we know that our green population of Sasquatches is twice as large as our yellow, how do we set these circles relative to one another? And I am going to show you slides here because the slides can show you the circles a lot better than I can hand draw here. But we need to know, what are we going to do? How are we going to represent that population in the east compared to the west? Well, the east is our smaller population, and out of personal experience of doing these, you want to set your smallest circle as your standard to do all your other circles from. In this case, we're doing 2. So you are going to do areas of a circle in order to figure out how big the circles need to be here so you can plot your populations. And you're going to use the smaller one as a guide. You can just pick a number. You're going to use the radius because any area you get from the circle is going to involve a radius, which is always RR. Okay, and you can make that radius your smallest circle, whatever you want it to be, it doesn't matter. I suggest you set that radius to something manageable and something reflective of the population. Like in this case, we are going to set our radius at, we're just going to use inches. Don't worry about it being in metric. It doesn't matter. It can be, if I did this in millimeters, the circle ratios would still be the same size, or centimeters. It doesn't matter. So we're going to use inches here, okay? So I have 50 of these guys. So my circle radius, it's not going to be 50 inches because that'll be hard to plot in Publisher, which is the program I use to generate these slides. But I am going to use my radius set at 0.5 inches, and that's a symbol for inches in case you don't know. So my radius is 0.5 inches. I'll just leave the inches off for you. Now I'm going to show you the incorrect way to do this first, because I've seen this done so many times. Now we already know we're going to use our radius and whatnot. So the area of any circle, regardless of its size, is calculated, but A area is equal to pi radius squared. So that's the equation we're going to use. Since our green Sasquatch population is twice as much, I could just be like, oh, let's set our radius equal to 1.0 inches. And our green here, because that is twice as much as this. And we would then draw our circles, and here is what they would look like next to one another. Is that green circle twice the size of that yellow one? No, it's not, because you're dealing with 2 dimensions. You're not dealing with 1 dimension. So that green circle is a lot bigger than it needs to be. Basically, if I took that green circle and divided it into 100 equal parts, and then divided that yellow circle into 50 equal parts, I would still have smaller yellow pieces. And that's not what I want. I want the pieces within the circles to be the same area. So this isn't correct. But how many times bigger is this green circle? Okay, so we can easily calculate the area of both of these circles here. Now we know we have 1 inch as our radius for our green Sasquatches. That's our radius. And for our yellow, I'm just going to use orange because it's easier to see instead of yellow. But if you see that, it's yellow. We have a radius of 0.5 inches as a radius. And we square that in both of them and multiply them by pi. I'm only carrying pi to 2 decimal places. It's all I need to do. It's not going to make that much of a difference. And in this one, since we're, 1 inch squared is 1 times 3.14, we get 3.14 and significant figures, 0 inches squared. So that is the area of our green circle. Now we do the same thing for our yellow circle, and it's not half as much. If it was half as much, this would be 1.5 something, I think. It would actually be, it would be closer to, okay, I think I got it. If this were twice the area of this, it would be, I think, about 1.57 inches squared. If it was twice this, all right? That's just me doing it quickly in my head. I'll correct it below if it's wrong. If it's not wrong, I can still do this stuff. But anyway, this is clearly a larger number. Well, how much larger? All we have to do to figure that out is get a factor like we did with the 100 divided by 50. We just take our green Sasquatches divided by our yellow Sasquatches. So we have 3.140 inches squared divided by 0.785 inches squared. And inches cancel. We can't have any decimals lingering that cancel. So we just divide these two. And the green Sasquatch circle that we drew using twice the radius is 4 times larger than the yellow one in surface area. So we gotta do something else. What are we gonna do? To keep things simple, we are gonna keep the area of our yellow Sasquatch circle at that 0.785 inches squared based off our 0.5 inch radius. But we need to do our green Sasquatch area now. And how are we going to do that? Well, we're going to base it off of this. We know what our area needs to be because our green area needs to be 2 times greater than our yellow area. So all we need to do is multiply 2 by 0.785 inches squared, and we get 1.57 about inches squared is equal to our area of green Sasquatches. So that's what we're going to use for this one. So what is our radius going to be? Because we know it's not 1. All right? So our radius is not known. And we're just going to algebraically manipulate this equation and then plug and chug. Okay, in order to solve for our radius, I'm taking this equation and we need to do some algebraic manipulation like I did with the sandstone block, trying to isolate pi by itself, except this time I have to isolate my radius. So I'm going to take my pi's, remember whatever I do to one side of the equation, I have to do to the other. I'm going to divide by pi on each side. That is going to cancel this out. Okay, and it's going to give me a number here. But I'm not done. This is a radius squared, not a radius. Well, how do I get rid of that square? Well, I take the square root of that radius. But since I did that there, I've got to do that here as well. And ultimately, I will just get the radius. Let's do a plug and chug here with the actual numbers in case you can't visualize this. So I'm just going to use our new area of our green Sasquatches as AG subscript 1. We have the area, we need to find the radius. So that is our area, and we set it equal to pi, which is 3.14, multiplied by our radius squared, which we don't know. And via the last algebraic manipulation, how do we solve for this? Well, we divide by 3.14 and 3.14 0.14. Now you can do the math as you go along, or you can do it at the end. I'm going to do it here as we go along. So this cancels and is gone. Well, it becomes a 1 actually. And anything times 1 is that anything. But we divide these two here and we get 0.5 inches squared. Nothing canceled. So that's just a coincidence that this 0.5 is the same number as this radius here. It's purely coincidental because of the ratios I'm using. All right, I'm trying to keep it simple. But we're not done. We have to get r by itself. So we just scooch it a little bit closer and we just take the square root of that, and that will not only get rid of our squares, but it leaves our radius as 0.707 inches. And I change this to an r now because that's our new radius. So our radius calculated for our proportional green circle is now 0.70 inches. So we know how big our circles are going to be now. And we look at this radius here, and it's almost 1.5 times as long as this radius here instead of 2 times as long. We look at the slide here, and you can see we have our 0.5 inches on our east side, which is our yellow Sasquatch population, and on the west side we have our green Sasquatch population. Down here at the bottom you see I did a diameter of 1.414. That's because in Publisher, when you do these, you have to use diameters to make circles, not radiuses, and so the yellow one would be 1, so I had to do the diameter. Now these two circles are proportional. Okay, that is what our circles should look like. They should look like they do here in this diagram, and kind of sort of like what I drew here. So that's why you need to understand what people mean when they say proportional. You need to know what dimension you're working with. Yeah, we live in a 3-dimensional world. We have no actual examples of 2 dimensions in our universe except maybe shadows. But we can represent things 2-dimensionally, like I did on the dry erase board here. So if I'm going to use something and say something is twice as large as something else in 2 dimensions, I need to use area, which is essentially the volume of a circle. And in 3 dimensions, I would use what we just usually call the volume of something. Would be the most accurate way to represent something, at least visually. Unless I was trying to represent mass as well. Because on a screen, you can't really represent mass. I mean, you can calculate what a sphere would be. You know, say you have 2 balls, all right? And now these are the same mass. And they're the same volume. But say one of these was more massive. And the result was that its volume was smaller. Just pretend that's still a perfect sphere. We would have to note that in our visual representation, because looking at something, there's no way to determine whether it is more massive or less massive than something else. I hope you enjoyed this 3-part mini-series. I was originally just going to do proportional circles, and I got to thinking, I'm like, you know what? People may not understand the concept of 1, 2, 3 dimensions, 0, 4, you know, and volume versus area and stuff like that, because I've seen proportional diagrams where they literally just make the radius proportional, then draw a circle around that. And that's not the way to do it, because as you've seen, you can get a much larger area than you actually need to represent what you have. In that last example there, if we cut that green circle into 100 equal sized pieces, they would be the exact same size as if we cut the yellow circle into 50 identically sized pieces. And that's what we were going for. That's what you want to do in a proportional chart or diagram like I demonstrated here for you with Sasquatch population. But anyway, I think that's it. At the end of this, after the credits, you will see the notes, the math's done on it. I actually do appreciate comments if I screwed up on something. I just want to say this real quick because I have some extra time for this video. I get a lot of comments saying you should film in this direction, or you should change the sound on this, or you should put the light over there. You know what? This comes out of my own pocket. I'm not a millionaire. I'm not a professional videographer or anything like that. I do this more for informational purposes than I do for aesthetics, special effects, and visual things as such. If you leave the comments and they're kind, I will let them stay. That's fine. I don't have a problem with that. But just keep in mind that this is for informational purposes. I'm not trying to win any awards with this stuff, all right? So if it's a legitimate mistake that you're pointing out, I have no problem with that. But keep the aesthetic stuff to a minimum, please. All right, and if you're nasty about it, I'm just gonna delete it. Okay, I'm done with that stuff. I've had it up to here with that nonsensical dribble. Okay, but anyway, if you have any legitimate questions or comments, please leave them below, and I hope you learned something.